In our previous investigation, we explored a specific geometric hypothesis that electric charge is physically a particle moving along a fifth-dimensional axis. That provides a clean architectural picture, but visual architecture alone cannot make physical predictions. To test this hypothesis against reality, we need quantitative coupling constants. This brings us to two variables governing our reality: the gravitational constant, g, and vacuum permittivity, epsilon naught. Currently, they sit on separate islands. Standard four-dimensional models lack a structural mechanism to merge them. Forcing them mathematically causes unit clashes, requiring arbitrary parameters. However, recent literature points to a different reality. The math shows a geometric coupling constant that permanently locks g and epsilon naught together. These dimensional constants emerge as the inevitable algebraic outputs of dimensionless five-dimensional geometry. Proving that physical constants originate from pure geometry is the ultimate test. If a five-dimensional theory is valid, it must derive these exact constants from scratch. To prove this, we will use a triangulation strategy, cross-examining three independent lines of research. Our three starting axioms are pure 5D geodesic geometry from Kim and Kim, kinetic transport theory from Sagaceta-Mejía, and macroscopic thermodynamics from Williams. Each of these frameworks uses distinct mathematical tools. The statistical probability of three separate systems producing the exact same algebraic structure by accident is effectively zero. These models were built by disconnected research groups, operating decades apart, with completely different goals. If all three paths lead to the exact same equation linking g and epsilon naught, it provides proof that this connection is a geometric necessity, not a mathematical coincidence. We start with the kinetic framework published by Sagaceta-Mejía and colleagues in 2017. They set out to model the thermodynamic fluxes of charged fluids. This equation is the foundation of their work. They took the standard Boltzmann equation, which describes the statistical behavior of particles, and embedded it into a five-dimensional manifold. We can isolate two main components here: the collisional kernel, representing particle interactions, and the velocity term, labeled v to the a. When they expand that five-velocity vector to account for the extra dimension, the classical Kaluza-ansatz natively emerges. The fifth component of that velocity explicitly defines the motion along the extra axis. It equals the particle's charge, q, divided by its mass, m, multiplied by a variable called xi. This denominator defines the variable xi, the coupling constant for the entire system. Expanding xi reveals its internal structure. It equals the square root of 16 pi times g times epsilon naught over c squared. Look closely under the radical. The gravitational constant and vacuum permittivity are forced together, operating as a unified geometric product. Because of this specific mathematical coupling, their framework derives the Lorentz force as a byproduct of space-time curvature. The force isn't added in, it falls naturally out of the geometry. The kinetic theory demonstrates that modeling basic particle transport in 5 dimensions requires fusing gravity and electromagnetism into one constant. Now we turn to our second paradigm, the thermodynamic framework published by Williams in 1980. This visual compares the two models. On the right, Williams derives his own charge-to-mass constant, called beta, from the consistency constraints between electromagnetism and gravity. To test if these two distinct frameworks found the same architecture, we will cross-check the algebra. By factoring the 16 pi out of the Sagaceta-Mejía equation, we extract a 4 over c, leaving pi, g, and epsilon naught inside the square root. This resolves to a precise algebraic match. The kinetic coupling constant z, multiplied by the speed of light, equals exactly 2 times the thermodynamic constant beta. This brings us to the third piece of the triangulation, Kim and Kim's 2017 geodesic deformation model. This matrix shows our three paradigms. In the bottom row, Kim and Kim approach the problem using pure geometry, defining the charge-to-mass ratio strictly as the rate of motion along the fifth axis. When you calculate the ratio of the Planck mass to the Planck charge using their geometric unit system, the output is exactly 1 over beta. The vertical alignment here is perfect. Beta and z perform the exact same mechanical function across all three models. Pure geometry, thermodynamic laws, and kinetic transport universally mandate the exact same fundamental 5-dimensional coupling structure. There is one theoretical detail left to address, identifying exactly where the 16 pi factor inside that coupling constant comes from. If we isolate the 16 pi and deconstruct it mathematically, it splits cleanly into 4 times 4 pi. According to Quincy's geometric theorem, that 4 pi is the exact measure, in steradians, of the solid angle of a complete sphere. This is why 4 pi appears in Gauss's law for electric fields. It is a strict geometric necessity for three-dimensional spatial closure, representing flux distributing outward over a sphere. When we translate this topology into general relativity, that exact same spherical geometry scales up, appearing as the 8 pi coefficient in Einstein's field equations. Finally, in the Kaluza extension to 5 dimensions, unifying the electromagnetic and gravity tensors structurally requires doubling that factor. 8 pi becomes 16 pi. This creates an unbroken logical chain, tracing the macroscopic coupling constant all the way down to the dimensionless topology of a simple sphere. The numerical constants governing the forces of our universe are explicitly dictated by the invariant geometric topology of 5-dimensional space. Theoretical algebra is necessary, but it requires empirical validation to prove it actually models reality. The Sagaceta-Mejía framework doesn't stop at pure geometry. They use this 5-dimensional substrate to derive standard, observable, macroscopic transport coefficients. This equation is the most critical physical output of their derivation, the Wiedemann-Franz relation. It calculates the ratio of thermal to electrical conductivity. This theoretical output perfectly matches a century of experimental data regarding heat and electrical conduction in actual metals. This geometric framework successfully predicts the measurable thermodynamic behavior of the physical world. We have successfully unified 3 completely independent lines of research into a single foundation. Kim and Kim established the pure geometry, Sagaceta-Mejía proved the kinetic transport, and Williams defined the macroscopic thermodynamics. Despite their different methods, all 3 pillars mathematically demand the exact same coupling structure. This completes the first tier of our analysis. We have established that the 4 pi factor is topology, the product of epsilon naught and g is geometry, and the charge-to-mass ratio is simply a velocity in the 5th dimension. With the geometric substrate verified, we have our foundation. The next phase of investigation uses this validated structure to decode the Williams viscosity framework.